All right, so today we have a relatively short lecture, but one that is filled with a lot of important information that relates to both physics and chemistry when we talk about metabolism. So the main part of today's lesson is going to be talking about thermodynamics and how they relate to metabolism. So if you recall from chemistry, if you already took chemistry, or if you're talking about physics, we're going to be talking about energy and movement of molecules and how they are compared relative to each other to see how fast reactions will occur. This is just because we know that in metabolism, in building and breaking molecules in living organisms, different processes take different amounts of time. And we have certain mechanisms that speed them up and certain mechanisms that slow them down in order to make sure that they work within our livable time frame. So for the do now, I'm going to explain it. I want you to do it, pause and do it, and then we'll go over it afterwards, just to see where you're at compared to where you should be, or if you are where you're supposed to be. So the prompt says, write a few sentences explaining what enzyme works in the stomach and what enzyme works in the small intestine to help you digest your food, aka the macromolecules that are supposed to be broken down. State your evidence and discuss using this graph. So in this graph, you can see that we have an enzyme called trypsin and we have an enzyme called pepsin, and they're both proteins because they are enzymes. And you see that pepsin works in this lower pH range and trypsin works in this neutral to basic pH range. And you can see that the rate of reaction is the highest for pepsin around 2 pH and for trypsin around 8 pH. So I want you to kind of pause and discuss and write down which one you think will work better in the stomach and which one will work better in the small intestine based on their maximum rate of reaction. So clearly, since the pepsin's peak or most optimal reaction rate is around 2 pH. 2 pH, remember, is below 7, and therefore it's an acidic environment, right? Between the small intestine and the stomach, we know that the stomach is full of stomach acid, right? Hydrochloric acid, and we know that it's extremely acidic in there to help you break down macromolecules. So if you want an enzyme to work in there, it's going to have to be the pepsin, because the pepsin works best at an optimal pH of 2. On the other hand, if you put trypsin into a pH of 2, it's not even going to work at all, because this little bell curve that shows how or where it works doesn't even reach over to this pH. So if you put trypsin into your stomach environment, it's not going to work at all. The enzyme is going to denature or change shape or even permanently alter so that it can no longer work ever again. Right. That means that if this one goes in the stomach, that means trypsin is the one that works in the small intestine, because the small intestine is a more neutral environment. So you're going to be around the 7s and the 8s in pH. And actually, that's where trypsin works the best. Okay. So this is how you would read this graph in order to tell and answer this question. So today we're going to go over some chapter 6 notes on metabolism, and it's a lot of reaction-based material. So we're going to be talking about which reactions release energy, which reactions require energy. And this is only important because, like I said, metabolism is literally just about building and breaking molecules. For your homework, you're going to finish off the baby essay that I will introduce at the end of this video. And I know it sounds weird, but it'll make sense when we get to it. And then your longer term homework is your chapter 6 summary and Learn Smart, which is going to be due at the end of the weekend, which is going to be Sunday. So our learning objective is that learners will be able to justify a scientific claim that free energy is required for living systems to maintain organization, grow or reproduce, and that multiple strategies exist in different living systems. So that being said, we're gonna move on and start off with the notes. So we're gonna go over some basic vocabulary. The first one is going to be kinetic energy. And if you've ever taken chemistry, then you already know that kinetic energy is simply the energy of motion. So when things are moving, they have energy in their movement. And that's what we describe as kinetic energy. So when molecules are moving, they have kinetic energy. When compounds are moving, they have kinetic energy. When you are moving, you have kinetic energy. On the other side, we have potential energy, which is stored energy in chemical bonds or energy based on a position. So the two examples are, for example, like glucose has a lot of bonds from carbon to carbon. And those bonds are basically just stored energy inside of that connection, that when you break it, the energy is released. And for example, we release it in order to gain energy to do other metabolic processes, right? We break down big molecules of glucose in order to get energy from those bonds and release them into kinetic energy. Another example would be energy based on a position. right? So if I am sitting at the top of a slope, I have potential energy. If I am in the middle of rolling down that hill or that slope, I have kinetic energy. So kinetic and potential energy are interchangeable because if you're moving, you have kinetic. If you're not moving, you have potential, right? You can have some of both, right? So if you're, for example, if you're on a hill and you're at the top here and you're resting, then you have the most potential energy and zero kinetic, right? If you are halfway rolling down, you still have some potential energy because you're not at the bottom yet, but you also have kinetic energy because you're partial way through your movement and you're moving currently down. And then when you reach the bottom, right before you hit anything and stop, you're rolling at your fastest speed and you have the highest kinetic energy, but you have zero potential energy now because you're at ground level, okay? A good way to compare kinetic and potential energy in my own head that I like to use is a glow stick. So before you crack the glow stick, it has the potential to give off light, right? It has potential energy, and light is energy in a sense. But once you have cracked the glow stick and you have broken that bond, then there's kinetic energy because it's using the energy and it's producing light. Okay, so that's just one way that I think of it. And if it helps you, that's good. If it doesn't, then it's okay as well. There are two laws to thermodynamics. The first one is that energy cannot be created or destroyed, only transformed. So the energy that goes into a molecule moving around really, really, really fast and having kinetic energy is the same exact energy that is stored in the bond when you connect those molecules together. So when that kinetic energy becomes potential energy, that energy is hidden in that bond. Okay, so it's changed either into a potential energy form or a kinetic energy form, but you never have new energy and you never get rid of energy. Okay, you only either move it to another place or you change its form. The second law of thermodynamics is that energy transformation is not 100% efficient. So you never have perfect transfer of energy. Some energy is always going to be lost as heat. And that's just because we don't live in a perfect ideal environment and because our processes like metabolism aren't perfectly enclosed in an environment and perfectly efficient. Okay, and that's just how the world is. And it's okay because we've already found ways to work around it. And usually we overcompensate to make sure that we will receive enough energy when whatever process we're doing by producing or breaking down more than we need to. And another reason is just because disorder or randomness is always increasing. So entropy down here, is the word for disorder. And disorder is always increasing naturally. For example, when a long time passes and a piece of concrete slowly crumbles into dust, right? Small particles of dust floating around is a lot more disorderly than one big slab of concrete, right? But over time, we always go towards disorder or more entropy. And I'll explain that in a second when we actually talk about Gibbs free energy in the formula. So an example of kinetic energy that I want to show here is sunlight. And the example of potential energy would be chemical bonds of food. So here's a molecule here where it's a carbon ring representative of part of a sugar. And that stores a lot of potential energy because it has a lot of carbon to carbon bonds. On the other hand, we have two molecules of carbon dioxide floating around and they move around a lot. So gases have a lot more kinetic energy and solids have potential energy. Okay, so liquids are somewhere in the middle. They have mostly kinetic energy because the molecules are still moving around. But gases have the highest kinetic energy because the molecules are literally bouncing off walls. And let's go over this a little bit. This should be kind of review for y'all, where we talk about the cycle of matter and photosynthesis and cellular respiration. So as you all know, the energy originally that powers photosynthesis comes from the sun, and that is light energy. And the organelle that the sun hits is chloroplast, and it is green, and it basically is green because it reflects all green light and absorbs all other colors of light. And you find these inside of producers or plants, or also known as autotrophs. And they do the process called photosynthesis to make oxygen and glucose. And then that oxygen and glucose is used up during cellular respiration by the mitochondria in animals. And right here it says heterotrophs, but we know that not only heterotrophs do cellular respiration, but autotrophs also do it. Okay, so all living things do this one with mitochondria, cellular respiration with mitochondria, but only some living organisms do photosynthesis with chloroplasts. And the whole point of doing cellular respiration is not to use oxygen or not to produce carbon dioxide, but the whole reason is to make ATP, which is our energy molecule, which will then be used up subsequently and turned into heat energy as a waste. Okay. The other wastes are carbon dioxide and water, which just so also happen to be the inputs for photosynthesis in the chloroplast. So it is a continual cycle where matter is never wasted, right? And it's kind of nice because matter is never created or wasted. So this cycle is continually going and going and going. And the only reason I want to mention this is because these are the main processes of metabolism, right? Building and breaking, as an example for the chemical reactions we're talking about. So here's the ATP cycle diagram. So the cell uses energy from reactions that release energy to produce ATP. So originally you have this molecule ADP floating around. Remember, ATP stands for adenosine triphosphate, and ADP is changed to adenosine diphosphate because right here you can see there are only 1 and 2 phosphates attached to this adenosine molecule. Right, so you're trying to add this third phosphate onto there to make it a high energy molecule. And in order to create that bond between the P's right here that you want to add on this third P, you're going to have to add energy in to this reaction. So you're going to have to produce energy and add it in so that it can be stored in this bond right here. Okay, so ATP formation, right, forming ATP from ADP is coupled with exergonic reactions. And I say is coupled with because the reactions have to be paired, right? This energy isn't just free floating around in the environment. That's not how energy works. This energy is going to come from another reaction that is releasing energy, right? So something is being broken. A bond is being broken in a second reaction where that energy all of a sudden that is released is going to be instantly put into this bond right here and stored again as potential. Okay, again, exergonic, I say, is a reaction that releases energy, right? So technically, this reaction right here is an endergonic because it stores energy. But the reaction that is producing this energy to allow you to store the energy is exergonic. So exer is releases energy or energy goes outside, right? Exer means out or leaving, okay? So then you produce ATP, you also happen to produce a byproduct of H2O, and this ATP molecule is now a high energy molecule that can be used to do the same process that happened here, but for other chemical reactions that might have to happen faster. For example, the cell uses the energy stored in ATP to power reactions that require energy input. So the energy put into here is a lot easier than the original reaction where it's going to be needed. So this one requires a lot of energy. And so that energy that was just stored in this bond right here is not going to be released to power another important reaction in metabolism. So here, you're gonna break ATP down and you're gonna add water, right? You don't have to add energy here because you're actually going to be releasing energy in this reaction. And when that P comes off, that reaction, that bond energy that used to be right here connecting to this P is now going to be released, and that energy can go into another chemical reactions bond, just like how it did over here. So again, ATP breakdown is coupled with endergonic reactions, or reactions that require energy. Because here, ATP breakdown is an exergonic reaction, right? It's releasing energy. So we have, for example, glucose being turned into carbon dioxide and water, right? So ATP breakdown is coupled with endergonic reactions. And remember, endergonic reactions need energy added, right? ATP breakdown is going to provide the energy by releasing it from that last bond with the P and then adding it as that energy. So you're going to be breaking down these big molecules from sugar and starches inside of an energy bar, and that's going to produce energy for you to use for actions. Okay, so ATP formation over here is coupled with exergonic reactions. And again, exergonic, remember, it means to release energy. And that release energy is going to be added into the reaction of ATP formation, which requires energy. So you can't actually make ATP unless you have some sort of energy source. And you can't do an endergonic reaction without having an energy source. So forming ATP is an endergonic reaction, and breaking down ATP is an exergonic reaction, but they're always paired because ATP is our free-flowing energy molecule inside of all living organisms. Okay, so there's like an unending cycle basically, because as long as you're living, you require ATP. And I say you, but I also mean like bacteria and plants and animals of all kinds, right? So when ATP is added with water, it breaks down the ATP into ADP, and energy is released for reactions that need the energy, or endergonic reactions. That ADP is easily recycled and attached to a phosphate again when you add energy to it to make that bond into ATP again to continue the cycle. So this reaction right here with the plus needs to require a little bit of energy added in. So this reaction is an endergonic reaction. So you have to add a little energy in to make sure that it gets back to this ATP molecule that we really need. So here's the visual representation of what exergonic and endergonic reactions are. So over here, we see an endergonic reaction, and you always require energy input because for all things, you're going to go up the hill and there's a little hump, and then you're going to settle where your products are. So this is the beginning of the reaction, right? See progress of reaction. You have your reactants, and you want to combine them. And combining them and creating a bond to get this product takes energy. So you're going to have to provide that extra energy and some more to get over that energy hump, and then the final product will sit at a higher energy level, at a higher potential energy level, okay? Because over here, we have a lot of kinetic energy, but over here, we have a lot more potential energy if you read this side right here, right? Because this bond now between the two of them has a lot of potential energy, but that energy has to come from somewhere, and usually it's gonna come from ATP breaking down into ADP. Exergonic reactions release energy, so products contain less energy than reactants. And again, like when we're saying this energy, we're always talking about potential energy here, okay? So if you take your reactant and you want to break it down, it's going to release energy because that bond energy now is going to be given up. The bond is no longer there. So it only takes a little bit of energy to get the reaction started, and then it will free flow by itself on and continue all the way to the end of the reaction by itself. You don't have to give any more energy. And usually this kickstart is super easy. It can even be kinetic energy. Some reactions, if you just tap the side of a bottle or a beaker, they will start automatically because the jostling of the molecules will just turn them straight into the beginning of the reaction. So this much energy is released when you take this molecule and break it down into its component products as the reaction progresses. So Gibbs free energy I showed you on the previous page. I also talked about some parts of it already with entropy. So Gibbs free energy is this formula right here. So you see delta G equals delta H minus T delta S. And delta G is just change in free energy, basically. Delta H is going to be enthalpy, okay? That's temperature related energy. So higher temperature is usually higher energy, and lower temperature is related to lower energy. And it's just releasing or intaking of energy that really changes the temperature of things. So for example, exergonic reactions, if you hold a beaker where an exergonic reaction is happening, usually that beaker will feel hot because the energy is being released. And when it's being released, your hand is absorbing some of it and it feels like heat. On the other side, endergonic reactions, if you hold a beaker that's doing an endergonic reaction or energy is going in, usually it feels cold because that energy is actually being stolen from you, the heat of your body heat from your hands. So you'll feel cold relative to the beaker because the beaker, the energy required for the reaction in the beaker is going to be taken from its environment, aka where your hand is touching it. Okay, so that's enthalpy related. And of course, temperature affects entropy because at higher temperatures, molecules bounce around faster, so there's more disorder. And at lower temperatures, even if the molecule is a gas, it's still gonna be bouncing around slower because the temperature is literally a measure of kinetic energy. And again, entropy, like I said before, is randomness, so disorder, right? I gave the concrete example before. It's the same thing as like if you have dominoes, it takes a lot of effort to stack them up because their natural state is to be fallen over and in a mess, okay? And eventually, even if you stack your dominoes or you stack your cards into really cool structures, they're more likely going to be falling over than staying in that structure or in that formation that you set them up in. And so when you do delta H or enthalpy minus T temperature times entropy delta S, then you get your Gibbs free energy. And Gibbs free energy is important because it tells you if a reaction is going to be endergonic or exergonic based on its positive or negative symbol. If it is negative, that means it's going to release energy, right? The reaction itself is losing energy because it's giving it away. It's going to be exergonic and it's spontaneous or happens instantaneously. Like I said, you can just tap the bottle and it'll start happening, or tap the beaker and it'll start happening. It takes almost no ignition to start. If it is a positive or delta G, or it is going to be endergonic, which means you got to add energy, right? Positive is add, okay? It's not spontaneous. You got to add the energy first in order for it to happen. Over here, we can kind of go over that ATP energizes target molecules to make them more likely to bond with other molecules. So for example, when you are building cellulose or you are building starch, you actually use, not you, for example, plants, when they're creating these energy storage molecules, they have to energize the molecules to make them willing to bond in the first place. So if you have a glucose and you react it with ATP, the ATP loses the phosphate and the energy bond, right? So that bond of the phosphate is now connected to the glucose in a process called phosphorylation, right? You're adding phosphate to a molecule. So you're going to phosphorylate that molecule. And that makes it easy for it to combine to the chain that's already been created because this bond energy is already stored here. It's easy to just move it over and then have it become the connection between these two as the phosphate then flows freely away to then maybe eventually reattach to the ADP. So phosphorylation is a super important process that happens in metabolism because without it, just releasing the energy from ATP isn't okay because then it's just free flowing energy and it's wasted and as heat, right? So if you contain it in a special steps like phosphorylating, it makes it easy for the reaction to proceed more smoothly and be directed to the correct location instead of just hoping that energy gets where it needs to go. So this is the baby essay that I was talking about that you're going to need to explain to me. So write a short essay explaining how a baby growing using energy coupling does not violate laws of thermodynamics. And so my explanation for this is basically, you know that babies are chaos. And raising a baby is chaos, or having a younger sibling is chaos. There's messes everywhere constantly, right? But as the baby is growing, it is becoming more orderly and more organized because it learns skills of organizations. It learns how rules work. It stops pooping its own diapers, right? Because you learn how to potty train, and it starts to know how to do certain ways of life. So it knows how to organize itself. It knows how to organize its thoughts. It knows how to organize physical things, like cleaning up the room after it's been disordered. So the older it gets, the less disorderly it is. But when it's younger, babies are super, super messy because all they do is cause messes, right? They'll create messes of toys, they'll poop or pee or barf everywhere, right? So that's creating messes for the people around in the environment to have to deal with. So that's kind of a coupling, right? Because as time goes on, disorder decreases and the environment is more ordered then, right? But as it starts off, the baby is super, super chaotic and has a lot of disorder around it. But inside, internally, as it creates disorder in the environment, inside it is becoming more orderly, right? So that's a pairing you're going to want to think about when you're writing this essay. That's the coupling, right? So the external environment is becoming more disorderly as the baby itself is becoming more orderly inside. And that's both like theoretically, like mentally and physically, because it starts to understand itself. So in this essay, you must mention both laws of thermodynamics. If you wrote them in your notes, you can reference them, but you can also just go back in the video to go check them out. I need you to redefine potential energy and kinetic energy for me. The coupling of exergonic and endergonic reactions. So you're going to tell me about how they're paired in an example regarding the baby's life. And then you're going to explain entropy increasing in total around the baby, right? The disorder around the baby increasing when the baby's in an environment. And then the baby itself, their entropy is decreasing. Remember, their disorder is decreasing inside of them as they grow and learn. So that's the baby essay. You're going to finish that up and then work on your chapter 6 summary and learn smart to make sure that you have that done by the end of the weekend.